Hello everyone, welcome to my second video on L'Hopital's rule. So we saw case 1 where we have the indeterminate form 0 over 0 or infinity over infinity, plus minus, doesn't matter. But now what we're doing is we're looking at the case where we're going to still apply L'Hopital's rule, but the indeterminate form that we're dealing with is 0 times plus or minus infinity. How do we deal with an indeterminate form of the form 0 times plus minus infinity? So the strategy is something I call use a flip. So the flip, what it is essentially it's noticing that x times y, you're multiplying two functions because you have something times plus minus infinity, so you're multiplying two terms, and you're gonna rewrite it as, if we want to flip the y, we could rewrite it as x over 1 over y. Why are we allowed to do that? Well, we don't usually go this way, we go from right to left. If you have x over 1 minus y, you could think of it as x over 1 divided by 1 over y. And we know when we're dividing fractions, you multiply by the reciprocal. You take the second fraction and flip it. So this is equal to x over 1 times, instead of 1 over y, it's y over 1, which is essentially just x times y. So we're accustomed going this way. But starting with the multiplication, we could rewrite it as x over 1 over y. Or another way you could write it is x over y to the negative 1. So you're going to drop the y and you're going to put it to the negative exponent. Okay, so we're allowed to do this. This is all equivalent. So this is what we mean, we're doing the flip. Why are we applying the flip? Well, in order to apply L'Hopital's rule, as I mentioned, we're going to reduce it from a case 2 to a case 1. In order to get a case 1, you need a fraction. Case 2, it's going to be a multiplication of two terms. You might not have a fraction, so using the flip, we transform something that has a multiplication to something that has a division, which is what we want because we want to take the derivative of the top and the derivative of the bottom. Okay, in order to do that, we need a fraction. The one issue with case 2 is, how do we know which function to flip? Do we drop the x or we drop the y? And this is something that's going to come with practice. There's no immediate answer. A trick that I could give you is that what you're essentially doing is you're looking at the exponents. So if you have something like x squared, think about if you take the derivative. Should you drop the x squared? Let's say you have x squared and you have, I don't know, ln of x. It doesn't really matter. Let's just focus on the x squared. The trick is if you're taking the derivative of x squared and you leave it on the top, the derivative would be 2x. Notice that the exponent is getting smaller, so it's slowly going away. And now the derivative, if you take it again, it's going to be just 2. So the x squared eventually disappears. Whereas if you were to drop it down and deal with 1 over x squared, and now you take the derivative of, let's say, x to the negative 2, because you dropped it. So you're dealing with x to the negative 2. If you take the derivative of x to the negative 2 now, what you're going to get is whatever's on the numerator, but on the bottom you're going to get negative 2 x to the negative 3. And if you take the derivative again, you're going to get whatever's on the top, it doesn't matter. You're going to get a positive 6, so negative 2 times negative 3, positive 6 x to the negative 4. Notice that the exponent is not disappearing, it's getting bigger. Negative 3, negative 4, negative 5, and you'll keep going on, and then you're going to get stuck. Okay, so looking at the exponent until thinking of the fact that if I take its derivative, it's going to disappear. That's one way of knowing which function to flip. But at the end of the day, it's going to come with practice. The more practice you do, the better you'll be at deciding which function to flip. And in the beginning, you're going to make mistakes. It's normal. But the more you practice, like I said, you'll have a better idea, intuition of which function to flip and which not. Okay, so let's go ahead and take a look at a couple of examples. So in this example over here, we have to use L'Hopital's rule to evaluate the following limit. The limit that's given is limit as x tends to negative infinity of x squared times e to the x. So we begin by substituting the value in. So we're replacing x with negative infinity. Here on the left side, we get negative infinity squared, so that becomes positive infinity times, and we have e to the negative infinity. E to the negative infinity, this is a common mistake that students make. They think it's infinity. Be careful. E to the negative infinity. We have a negative exponent, so that actually drops it. 1 over e to the infinity. Right? And 1 over e to the infinity is 1 over e to the infinity is just infinity. Right? E is 2.7. And that number to the exponent infinity just takes off to infinity. So we have 1 over infinity, and we know that 1 over infinity, or dividing by a very large number, makes the whole number small. So that's essentially 0. Okay, so we have infinity times 0. This is the indeterminate form that we're dealing with. So we're dealing with a case 2. We have to flip one of the functions. Okay, so before applying L'Hopital's rule, you're just flipping. So we're going to reduce this to a case 2. from a case 2 to a case 1. So limit as x goes to negative infinity of x squared times e to the x. We know it's a case 2, therefore we have to flip one of the functions. Again, which function should we flip? Should we drop the x to the 2 or should we drop the e to the x? What's your decision? Try. Sometimes both of them work. Sometimes one's easier than the other. Again, this comes with experience. I'm definitely dropping the x to the negative 2. Oh, sorry, not the x to the negative 2. I'm dropping the e to the x. Why? If we leave e to the x on top and you keep taking the derivative of e to the x, is it going to disappear? No, because the derivative of e to the x is e to the x and it stays. It doesn't disappear. So I'm going to drop this, get rid of it, because I know if I keep the x squared on top and I take the derivative of x squared, as I mentioned earlier, the derivative of x squared is going to be 2x, and then the derivative of 2x is going to be just 2, and eventually that x squared is going to be gone. So that's why I know that I'm going to drop the e to the x, okay? Or that's at least my game plan. If you want, you could try dropping the x squared. It might work. I don't think so, but you never know. So I'm going to rewrite this as limit as x tends to negative infinity of x squared on top over e to the negative x. This is the way I'm writing it. This is the notation I'm using. I rather use e to the negative x opposed to 1 over e to the x. Because if you're using e to the negative x, you're using chain rule. Whereas if you're doing 1 over e to the x, you're applying quotient rule. Okay, so you're going to apply quotient rule on the bottom. Both ways are fine. Okay, I prefer chain rule, so I'm going to use e to the negative x. I think it's easier. Okay, and now we have our fraction, and now let's reevaluate the limit. If we plug in negative infinity on the top, we have negative infinity squared, which gives us infinity. And on the bottom, if we have e to the negative of negative infinity, becomes two negatives turn into a positive. We have e to the infinity, which is infinity. So this is the indeterminate form, infinity over infinity. So we reduced it from a case 2, infinity times 0, to a case 1, infinity divided by infinity. So we could apply L'Hopital's rule. And we have the indeterminate form, infinity over infinity. Okay, which says to take the derivative of the top and the bottom individually. So limit as x goes to infinity. The derivative of the top, as I said earlier, is 2x. And the derivative of the bottom, oops, sorry, not infinity. Limit as x goes to negative infinity. That's a mistake. And on the bottom, the derivative of e to the negative x is negative e to the negative x. Okay, so that didn't really help. We plug in x going to negative infinity. On the numerator, we get negative infinity. And on the bottom, we get negative, negative, positive e to the negative infinity. So we get negative infinity over negative infinity. So again, we could apply L'Hopital's rule. The two negatives cancel, giving us infinity over infinity. Okay, so we take the derivative of the top and the bottom, so let's keep writing our limit. Limit as x tends to negative infinity. The derivative of the top is 2, and the derivative of the bottom, negative e to the negative x. Using chain rule, it becomes positive e to the negative x. Okay, substituting the x with negative infinity, we get, so now we won't get an indeterminate form because the numerator is 2. So we get a number. So we're essentially done. We get 2 over e to the negative of negative infinity. Okay, this gives us 2 over negative, negative turns it positive, 2 over e to the infinity, which is 2 over infinity. And again, a number divided by a very large number, infinity, gives us 0. And this is the answer to this limit. We're done. Okay. So multiplying 0 times infinity is not always going to give us 0. It depends on the functions. Is the function tending to infinity quicker, or is it tending to 0 quicker? This is the question that we're asking us. In this specific case, it went to 0 faster. Okay, let's keep looking at examples. So in this example over here, we have to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side of x squared times ln of x. So pause the video and see if you could solve it on your own, and compare your answer with mine. So first, let's substitute x with 0 from the positive side. 0 from the positive side squared is still 0 times ln of 0. Remember, ln of 0 doesn't exist, but if we consider the function, a value that's really close to 0 but slightly to the right, logarithms go to negative infinity. Okay, so this is the indeterminate form, 0 times negative infinity. So we have a case 2. We have to reduce it to case 1 by flipping one of the functions. You have to decide which function to flip. So I don't know which one you chose, but the one that I'm going to choose is the x squared. I'm going to flip the x squared and bring that down. Why? My reasoning being is that I know when I take the derivative of ln of x, we're going to lose the logarithm and we're just going to 1 over x. So we're dealing with, let's say, a rational function opposed to logarithms. Okay, so that's my game plan. Let's go ahead and try it. If you drop the ln of x, I think it might still work because your x squared is eventually going to disappear. but I think it's easier to drop the x squared, just in my opinion. So let's go ahead and do that. So I'm going to rewrite this as the limit as x tends to 0 from the positive side. I'm going to write ln of x over x to the negative 2. So I'm dropping the x squared, and since I dropped it down, the exponent becomes negative. And now we're going to evaluate the limit. So plugging in x as 0, what we get is log of 0 to the positive side. This is a plus. So this gives us negative infinity. And on the bottom, if I plug in 0, 0 to the negative 2, x to the negative 2 is 1 over x squared. And now it might be a bit easier to see. Since it's not 0, it's a value that's really close to 0, just slightly bigger. This is like 0.00001, a very small number close to 0. So when you're dividing any number by a very small number, this thing explodes to infinity. So we have infinity, well, negative infinity over infinity. Okay, so let's keep going. So we could apply L'Hopital's rule. We reduced it down to a case 1, infinity over infinity. Let's apply L'Hopital's rule by taking the derivative of the top and the bottom individually. Notice that I keep writing the limit in the front, so don't forget that. Keep writing the limit, and the derivative of ln of x is 1 over x. And on the bottom, the derivative of x to the negative 2 is negative 2 x to the negative 3. Okay, so this might look a bit more complicated, but by simplifying this, it's not too bad. So before you evaluate the limit right away, simplify this. What we have is 1 over x divided by negative 2 over x cubed. So I dropped the x to negative 3. And now it's x to the positive 3 on the denominator, and we have a fraction divided by a fraction. We know when we're dividing fraction, we multiply by the reciprocal. So this is equal to limit as x tends to 0 from the positive side of 1 over x multiplied by, instead of negative 2 over x cubed, it's going to be x cubed over negative 2. Okay. Notice that one of the x's cancels with one in the exponent, giving us the limit as x tends to 0 from the positive side of x squared over negative 2. And now we're just substituting x with 0. Notice on the bottom you don't have 0, so it's going to be 0 squared divided by negative 2, which is essentially just 0. And we are done. So again, this one here tends to 0 faster than it tends to infinity. Okay, so the limit of this function x squared times ln of x is 0 as x tends to 0 from the positive side. So in this example over here, example number 3, we have to use L'Hopital's rule to evaluate the limit, and the limit that's given is the limit as x tends to 0 from the positive side of cot of 3x times sine of 6x. So as always, pause the video, try this on your own, see if you get the same answer as I do. So the first things first, we substitute the x value with 0, plug it in, what do we get? So cotangent of 3 times 0, so cotangent of 0 is infinity. Yeah, because cotangent is the same as 1 over tan of 3x, which is 1 over tan of 0, which is 0. But since it's 0 to the positive side, it's not exactly 0, it's a number that's very close to 0, but on the positive side, so 0.00001. And we're dividing by a very small number, which explodes the number, makes it go to infinity. Okay, so we have infinity over here, and then sine of 6 times 0, so sine of 0 is 0. So we have the indeterminate form infinity times 0. Again, these are case 2 problems. We have to reduce it down to a case 1 by flipping one of them. Okay, so here we don't actually have to apply the flip, we could just apply a property. The property being, using our trig information, we could rewrite cotangent as sine of 6x over tan of 3x. We know the reciprocal of cotangent is tan, so we could just drop it down and call it tan. And now here we have our division, and we could apply L'Hopital's rule. We dropped it down, we reduced it from a case 2 to a case 1. Substituting x with 0, we get sine of 0, which is 0, tan of 0, which is 0. So we have the indeterminate form 0 over 0. So we could apply L'Hopital's rule. So I'm stating now I'm applying L'Hopital's rule, meaning I'm taking the derivative of the top and I'm taking the derivative of the bottom individually. Again, remember, do not apply quotient rule. If you have a division solely in the denominator or solely in the numerator, then you could use quotient rule. But don't use the whole thing. Like, focus on the numerator and focus on the denominator on its own. Super important. So the derivative of the top, just the sine of 6x, is cos of 6x times the derivative of the inside, which is times 6. And the derivative of tan is secant squared of 3x times the derivative of 3x, which is 3. Okay. And now we substitute the limit. So the limit as x goes to 0. Replacing x with 0, we get cos of 0, which is 1. So on the top we get 6, and on the bottom replacing the x with 0, we get secant squared of 0, which is also 1. Times 3, you get 3, and 6 divided by 3 is just 2. So the answer to this limit is 2. So notice that we had a multiplication of 0 times infinity. So one was going to 0 and one was tending to infinity. Which one went faster? Well, they kind of met in the middle, or not met in the middle, but they met at an actual finite value. So the infinity and the 0, it didn't actually win. It's not always going to be either 0 or infinity. It could actually meet at a finite value in between. Okay. So example number 4 here, we have to again use L'Hopital's rule to evaluate the limit. The limit that's given is limit as x tends to 0 from the positive side of x times ln of x squared. So the square is hitting all of the ln of x. So this is very similar to an earlier problem that we saw. So again, pause the video to see if you get it on your own. The other thing I just want to mention is the square is not in the exponent of the x, so you can't drop it down in front, okay? So let's begin by evaluating the limit. Replacing x with 0, we get 0 times ln of 0 from the positive side we know is infinity. Well, it's negative infinity, and we square it, so it becomes positive infinity. So we have the indeterminate form 0 times infinity. Okay, so let's evaluate the limit. Sorry, not evaluate. Let's reduce it down to a case 1. Right now we have it in a case 2. Let's reduce it down to a case 1 by flipping one of the functions. Which one do we flip? Well, my game plan is to flip the x. Let's get rid of the x. So we're not applying L'Hopital's rule, so it's a regular equal sign, and we have ln of x, all that squared, divided by x to the negative 1. Okay. You might be able to drop the ln of x, all that squared. It might work as well, and it might be easier, but I'm going to do it this way. At the end of the day, we'll get the same answer, so it doesn't matter. Substituting 0 plus, we get ln of 0, yeah. So we have infinity over infinity. And now we can take the derivative of the top, so we get 2 times, oops, sorry. Common mistake, don't forget to write the limit. Derivative of the top is 2 times ln of x times the derivative of the inside, which is 1 over x, over the derivative of x to the negative 1 is negative x to the negative 2. Okay. So before we use L'Hopital's rule again, let's simplify this. Do it down here. We get the limit as x tends to 0 from the positive side of 2 ln of x divided by x, all that divided by negative 1 over x squared. Now we're going to flip it, giving us the limit as x tends to 0 from the positive side. Flipping this, we get 2 ln of x over x times x squared over negative 1. And notice that one of the x's cancels with, one of the x squared cancels with the x's. So this leaves us with no division, just negative 2 times ln of x times x. Okay. But again, we need a division in order to apply L'Hopital's rule, so we're going to drop the x again and deal with x to the negative 1. So that's equivalent. And now we could apply L'Hopital's rule. So if you plug in 0, again, we get this is negative infinity times negative 2 is positive infinity. And 0 plus, like 1 over 0, is infinity. So you're dividing by a very small number, makes the whole thing big. So we have, again, L'Hopital's rule, the indeterminate form of infinity over infinity. So we take the derivative of the top, take the derivative of the bottom, and we get negative 2 over x divided by negative 1 x to the negative 2. And this we just simplify. Limit as x goes to 0 from the positive side, we get negative 2 over x times this, you can think of it as negative, again, negative 1 over x squared, and we're going to flip it, giving us negative x squared over 1. So the two negatives cancel, and x squared divided by x is just limit as x goes to 0. It's just 2 negatives, 2 is still there, we get just 2x. Replacing x with 0 gives us 0, and this is the final answer. We're done.